So, after placement comes the process of routing. So, from today onwards we shall be looking at some of the different techniques and algorithms that are used for solving specifically the routing problem. But before going into the algorithms as such, let us first try to understand what this problem of routing really involves. Well, as you can understand by its name, routing means interconnecting the different signal pins of the components on the surface of silicon, well, so as to interconnect them. That means with respect to a net list, you will have to connect them. Now, the problem is not as simple as it looks like, because you try to understand on the surface of the chip there may be thousands and thousands of such modules. There is no guarantee that one module will be connecting only to modules which are in its neighborhood. It may be possible that two modules which are far apart, they also need to be connected. So, exactly how will the path or the routing path be decided or be found out? So instead of treating the problem as one and trying to solve it in one go, it is normally tackled in a hierarchical fashion. There is a process called global routing, where we look at the global picture and try to find out a rough strategy using which we will be carrying out the routing. Then there is a process called detailed routing, where based on the strategy we have just decided, we will try to complete the detailed interconnecting, means interconnection paths will be exactly finalizing the exact places where the routes or the wires have to be laid out. Now, before going into those algorithms, we look at a generic routing problem which is called grid routing. First look at some algorithms for grid routing, then later we will find out that exactly where this grid routing fits in the overall picture of the routing problem. So, we start today by having some discussion on the so called grid routing. Now, as the name implies, you can easily understand that we are talking about routing in some kind of a grid structure. Okay. So, let us try to see what grid routing really is, but first let us look at the general problem once more. The process of routing will obviously follow the process of cell placement in the VLSI design cycle. Now, when we say that we are trying to carry out routing, we are actually trying to find out the exact or the precise paths through which the conductors will be carrying the signal from one point to the other. For example, if this is one pin of a block, this is another pin of a block, well, we may have to route the signal like this if there are obstacles in between. This may denote the routing path. Well, if there are some obstacles in between, you cannot have a straight Manhattan path, minimum distance one. Now, this problem of routing is important because not only it takes up a substantial percentage of the total design time, it also takes up a substantial percentage of the layout area. Well, this percentage can be as high as 50% if your placement is not good. So, as I said, we look at a subproblem called grid routing to start with, then we will be looking at the different subproblems and going into the detail slowly. Now, in grid routing, the problem is simple. Here the layout surface where we are trying to carry out the routing or the interconnection, that is assumed to be made up of a rectangular array of grid cells. This is the assumption in case of grid routing. So, the whatever be our surface, we divide or split the surface into imaginary rows and columns. Those are our grids. Okay. Now, in that imaginary array of grid cells, some of the grid cells can act as obstacles, because all of them are not free for routing. Now, obstacles can be of two types. There can be some blocks which are the circuit cells. So, circuit cells can be treated as obstacles on the surface of the grid, and some of the interconnecting nets which you have just laid out that will also be acting as an obstacle for the future laying out of the nets. So, some nets which are already laid out, they will also be acting as obstacles. Now, in grid routing, our objective is to find out a path connecting 2 points, and means obviously belonging to the same net. So, one characteristic of grid routing is that we consider 2 points at a time. The basic grid routing algorithms, they consider the sub problem of connecting 2 points one at a time. This kind of sub problem is taken one at a time. We have only 2 points, we have to connect them. Broadly, grid routing algorithms can be classified as either maze routing or line search algorithms. We will be looking into these in detail. Okay, first, whatever we are saying that the array of grid cells, some blocks or the nets can act as obstacles. I have a diagram to show you exactly what I mean. This is just a diagram for the sake of illustration. You see here the total floor area we have divided up into some rows and columns. The black regions, these are the obstacles. These may be already pre-placed cells or they may be interconnecting wires. This is the these are the 2 points you want to connect. This is source S and the target T. And in this hatched area, I am showing one possible path. This is one possible path through this grid structure. So, when I pose this sub problem that given a set of obstacles placed on this array of grid, given a source grid cell and a destination or a target grid cell to find a path, actually we will have to find out a sequence of empty grid cells which will lead us from S to T. Now, obviously, this is not the unique path, there are other paths also, this may be better or this may be shorter length also possibly. So, there can be multiple paths to it. So, the problem of grid routing attempts to find out one path. Well, we will want that the path is as good as possible, if possible minimum cost. There can be other nets also which will be acting as obstacles. In the order in which you lay out the nets, that also becomes very important, because once you lay out net number I, that will act as obstacle for net number I plus 1. Okay. So, the problem definition is, well, in case we are basically talking about the grid routing for the time being, we have a set of blocks with pins on the boundaries of the blocks, a set of signal nets and the precise location of the blocks which have been fixed during placement, right. Our objective is to find suitable paths on the available layout area space. So, the space which are already taken up by the blocks, they are not available for the interconnection obviously, and we will have to minimize some objective function while we are trying to carry out the interconnection. Now, this objective function or the constraint can be of different types. Well, we basically need to take care of several kinds of constraints when we are trying to complete the routing. Some of the important constraints are like this: minimum width of routing wires. Well, if you look at the VLSI design layout level, there you may be knowing that signals may be carried on several different layers. Of course, metal layer is an option, but for shorter distances you can even carry signals over polysilicon or diffusion layers. Now, to the VLSI designer, some of this process of laying out the basic cells on the surface of silicon and interconnecting them, this has been simplified by framing or formulating a set of geometrical design rules. The idea is that if your layout follows those geometrical design rules, then your circuit will work correctly. These are some some kind of rule of thumb, like I am giving some examples. Well, all measures in terms of the layout are computed in terms of a basic unit called lambda. Lambda is synonymous to the channel size. Typically the channel length is equal to twice lambda. Now, some of the design rules says that if it is for example polysilicon line which is carrying a signal, then the minimum width of the polysilicon line has to be twice lambda. If it is a metal line, if you are carrying signal over a metal line, then the width has to be thrice lambda. Now, these figures have come up from the accuracy with which you can do fabrication at the different levels from experience. Not only are the width rules given, also some separation rules are given. Like if there are two polysilicon lines which are running side by side, what will be the minimum separation between them? If a polysilicon and a metal line are running side by side, of course on two different layers, what should be the minimum separation between them? So, all these design rules have been framed up. Now, you have a set of such geometrical rules and any layout will have to conform to those rules. So, means when you are doing interconnection, you must keep those in mind. So, you cannot run a very thin interconnecting line which is not conforming to the design rule. Metal, the minimum width of the line should be thrice lambda, for example. Right. Of course, other constraints are there, how many routing layers are available to you, this will be given as input, and if there are any timing constraint, the critical nets have to be given priority.
Lambda is the channel length?
Actually, twice lambda is the channel length, lambda is half the channel length. Okay. Well, the reason I am just mentioning this constraint is that, well, when we are talking about this grid routing, so we are saying that the layout surface is divided up into rows and columns, right. So, it will be a big grid. Now, the idea is that the grids or the sizes of the grids are chosen in such a way that if required I can lay out two different wires on two adjacent rows, which means that my width or the height, whatever you call, of these grid cells must be at least equal to the minimum width plus the minimum separation of the lines, so that two adjacent rows or columns can carry two different signal lines belonging to two different nets. This is the way we select the size of the grid cells. Okay. So, now let us come to the grid routing algorithm. So, we had said that maze and line search algorithm are the two broad categories. Well, of course, Steiner tree kind of algorithms also exist, but due to its complexity people very rarely use it. Maze running and line search algorithms are most popular. So, we would be looking at some of the important representatives of these algorithms, algorithm classes, Lee's, Hadlock's, Mikami-Tabuchi and Hightower's algorithms. So, we start with maze running algorithm. Well, maze running algorithm, you must have solved some maze kind of a puzzles where you enter the maze from one point, you have to come out of the other point, you have to find a path through it. So, the idea is something like this. Well, like here also you have a source, you have a target, you have some obstacles in between, you will have to find out a path, some kind of a search. So, the idea behind maze routing algorithms is exactly that. So, for the grid routing, the entire routing surface we represent by a two-dimensional array of grid cells, right. Now, when we say that we represent it by a 2D array of grid cells, this means that all the pins of the components, they must be aligned to the boundaries of the grids, all the wires, they must be laid out with respect to the grid boundaries, and the edges of the bounding box that represent the blocks, they also must fall on the boundaries, which means that the size of the grid will act as some kind of a basic unit. So, everything will be aligned with respect to the grids. Okay, so, a block cannot go halfway into a grid cell, it will either occupy a grid cell wholly or it will not occupy. This is the idea. The segments on which the wires run are also aligned, everything is aligned, I mean to say. And as I have just mentioned, that the size of the grid cells are also appropriately defined, so that wires belonging to different nets can be placed or routed through adjacent cells without violating the minimum width and separation constraints. So, accordingly we fix up the size of the grid cells. Now, one characteristic of mesh routers is that, just as I have just mentioned before also, that it connects a single pair of points at a time. It does not look at the global routing problem and tries to solve it, it takes one small sub problem at a time. Given 2 points, it tries to connect it. So, as I said, if it is represented as a 2D array, so actually we have to find out a sequence of adjacent cells which will lead from the source to the target. This is my objective. So, first we look at the most popular algorithm in this category, the Lee's algorithm. So, Lee's algorithm was one of the first algorithms which I proposed. It is a classical algorithm in that sense. Now, some of the characteristics of Lee's algorithms are, well, the first thing is that it is based on a breadth first search strategy, and this method is optimal in the sense that, firstly, if a path exists between source and target, it will always be found. Secondly, it will always find the shortest possible path. So, in this sense, Lee's algorithm is optimal. See, the reason it is optimal, it is not very difficult to understand. Once we explain the algorithm, you will immediately see, because it tries to explore all possible paths in parallel. The first path which touches or hits the target, it is the one which is chosen. So, since you are exploring all possible paths in parallel, so if a path exists, it will be found out, and the first path to hit will be the minimum cost path. Okay, fine. Now, the characteristic of Lee's algorithm is that if your grid size is h by w, then the time complexity of this algorithm is order h into w, and also the amount of memory requirement, the space complexity, is also h by w. Okay. So, we will see how, because the basic data structure you are using is a 2-dimensional array of size h by w. That is why the space complexity will be h by w. Yes. Number of rows and columns. Yes. Now, Lee's algorithm actually works in 3 different phases. First, let us look at the phases and then we will take an example to work it out. The first phase of the algorithm performs something called wave propagation. Well, this is called wave propagation because starting from the source, as if we are emitting or starting to emit some kind of an wave front in all possible directions, and with each step the wave front advances one cell at a time. So, just through all possible available paths, the wave front will try to expand in all directions. The idea is that sometime this wave front will be hitting the target. Okay. So, let us see what this wave propagation phase consists of. Well, this is an iterative process, because I told you it in each step it is advancing one step, that is why it is iterative process. Well, during the wave propagation phase, what we do, we label the empty cells in the grid array by some numbers 1, 2, 3, 4. The number indicate during step number I, we will be putting the number I. During step 1, we will be labeling some of the cells with 1. During step 2, we will be labeling some of the cells as 2, and so on. So, during step I, we will be labeling them as I, some of the cells. During step I, all non-blocking grid cells at a distance of I from the source, they will be labeled with I. This is how the labeling is carried out. So, all possible cells from the source which are at a distance of I, subject to the obstacles of course, they will be labeled with the number I. This is how the labeling is carried out. This labeling will continue until the target cell T is reached, say in step number L. Well, if T is reached in step number L, it means that L is the length of the shortest path, right. The process will fail if either of these two things happen. When you see that beyond a point you cannot label any cell any further and you have not yet reached T. So, no path exists to T. T is not reached and no new grid cells can be labeled during some particular step I. Or secondly, well, if the user also specifies some upper bound to the path length, say m, you see that even after iteration number m, you do not find a path to T, then also you stop with failure. So, under these two conditions you do not find a path. So, the first step of Lee's algorithm is wave propagation, whereby starting from the source you are systematically going on labeling the grid cells 1, 2, 3, 4 sequentially with numbers till you hit the target. Okay. Yes.
I plus 1, I plus 2, do they form concentric rings?
Some kind of, actually without any obstacles it will look like a diamond expanding, it will look like a diamond shaped thing.
So, what happens when you meet an obstacle?
I will take an example. If you meet an obstacle, you do not label the obstacle cells, you try to find out the other cells which are free. I will show an example. Okay, the first phase is wave propagation. Well, once you hit the target, the next step is to systematically trace back from the target and find out one possible path. There may be multiple paths. So, you try to do a retrace and find out one of the feasible paths, because all the paths that you will be getting retracing from the target, well, if the target is labeled as L, so all the paths will have a length of L. The retrace phase for Lee's algorithm is very simple. Well, you systematically backtrack from T back towards S. Well, the idea is that if the target cell T was reached during step I, what does that mean? That the target cell T was labeled with some number I. Some of the neighboring cells must have been labeled with I minus 1. So, you select one of the neighboring cells which are labeled I minus 1. Similarly, from I minus 1 you select one of its neighboring cells which was labeled I minus 2, and so on. Finally, you will be reaching some cell which will be labeled as 1, that 1 is adjacent to S, you have reached S. Okay. Because the way you are carrying out the labeling, given a cell with a label I, you will always find a neighbor with label I minus 1, because it was from that neighbor only you came to this cell.
You are doing some DFS in the Part-VIII.
Yes, DFS, yeah. No, during retrace we are doing DFS, he is right. Because during backtrack we are interested in selecting only one path, we are not interested to look at all paths. Yes. So, by tracing these numbered cells in descending order, we can reach S, and any path you follow, that will be the shortest path. Because starting with the number L, you are going to L minus 1, L minus 2 back to 1, all paths will have a length of L. But some of the paths will be more desirable than the others. So, there is a rule of thumb while you are backtracking, that you do not change direction until it is necessary, unless it is necessary, because zigzag wiring is not very desirable while interconnecting. Well, if you can find a straight line path where numbers are descending, try to follow that straight line. So, in general there will be a choice of cells which you can follow during backtrace. So, you try not to change the direction of retrace, this is a heuristic. this will minimize the number of bends in the wires. Minimize number of bends means your reliability will increase, because more the number of bends there is a chance of the junction getting thinner.
So, sir, when you go for a straight line,
Yes.
on a straight line you may go from one layer to another and from the other layer down. So
Right now we are not talking about layer, we are assuming there is a single layer routing.
contacts.
No, here in Lee's algorithm we are treating, we are assuming there is a single layer, there is no concept of multiple layers right now. There is a single grid array through which we have to carry out all the routing. Multi-layer thing will be coming to later. Yes.
So what's the need of backtrace? We can find the path in the forward.
Forward trace, I will work out an example, that means you will get an example, you will get your answer. Well, now after retrace you will be getting one path, but during the forward trace you have made the array dirty, you have labeled so many cells with the numbers. So, before you start connecting another pair of points, you will have to clear those numbers, then start it again. So, the third step is the so called label clearance step. Just other than the path you have just found out, the other labels which you have temporarily put in, they will have to be cleared. So, all labeled cells except those corresponding to the path just found, they will have to be cleared or initialized to some value. This also is an involved process. The search complexity is almost as high as the forward propagation phase, wave propagation phase. So, these are the three steps of the Lee's algorithm. So, let us take an example and work out, so that if you have any doubts, it will get cleared. Okay, let us take this same example. These are the obstacle cells. This is our source, this is the target. So, we start with the source. The neighboring cells of S other than the obstacles will be labeled with 1. So, this will be 1, this will be 1, this will be 1. These are the 3 neighbors. Next step, all the neighbors of 1s will be labeled as 2s. So, that you will have to maintain some kind of priority queue through which you will be doing this breadth first search. So, this will be 2, this will be 2, 2, 2 and 2. Then the neighbors of 2s will be labeled as 3s. This will be 3s. This 2 has stuck obstacles on all sides, it cannot expand any further. 3, 3. Then 4. So, you come 4, 4, 4. Then 5. 5, 5, 5, then 6, 6, 6, 6 and 6, then 7, 7, 7, 7, 7. Then while trying to label 8, you will hit upon the target. So, target is at a distance of 8 from the source. So, from this you can follow, since there are a number of choices you have 8, 7, 6, 5, 4, 3, 2, 1, you can follow a path like this if you want. If you want, you can follow a path like this also, because this is also a feasible path 7, 6, 5, 4, 3, 2, 1 is. But as I said, it is better to minimize the bend. So, this will be a more desirable path. So, this is the basic idea behind Lee's algorithm. This is how you carry out the labeling, and after this labeling is done and this path has been fixed out, you mark this entire path as an obstacle for the next step. This entire path will be marked as an obstacle now.
So, you said that don't change the direction until necessary.
Yes.
So, like after 4, there is a 5 on the left.
But after 4 you will have to go to 3, you are always moving to a lower number. 5 is not a choice available. Yeah. Yeah, from I you will be moving to I minus 1 always. If a neighbor is labeled by some other number, that is not a candidate for visiting, you do not go that direction. Okay. So, this is the basic concept behind Lee's algorithm. It is very simple, to implement, but of course you can see that this is very complex in terms of the memory requirements and the number of cells you expand or label. Now, let us just look into the complexity of this method, first with respect to memory, then with respect to the computational steps you require. Well, first you look at the memory requirements. So, of course, well, in terms of the rows and columns, well, if it is an n by n array, of course you require an n by n, this require n by n array to store it, but each element of the array, how many bits you require to represent, that is one issue. So, you just look at the memory requirement critically. Now, suppose the user have specified L as a bound to the maximum path length. Well, if the user have not specified anything, then if it is an n by n array, then in the worst case L will be of the order of twice n, because if the two cells are in the two diagonally opposite corners, the path will be equal to twice n minus 1, that length. But user can specify some other value less than that also, because I want paths only with a maximum length of this. So, if this L is given by the user, then the maximum label you can put on a cell is L. So, the valid labels are between 1 and L. Now, in addition, you also have to indicate the empty cells, also have to indicate obstacles. So, you require two other bit combinations. So, actually L plus 2 different things you have to store. Suppose I have certain number of bits, there will be one bit combination which will be indicating empty cell, maybe 0, there will be another bit combination which will be indicating blocked or obstacles, and other bit combinations can be used for labeling. So, actually we need log L plus 2 so many bits per cell, actually ceiling of that. Yes.
Why 2n plus 2?
Huh?
Why 2n there, sir? For
2n?
n by n cell, they can also be part that is zigzag. And
Zigzag, whatever you do, suppose you have your source on this side and target on this side, there your Manhattan distance can never be less than 2n minus 1. Whatever do you follow? Diagonally you cannot go diagonally.
so but you can do more than 2n also, because
Huh?
if you have part which is like this, okay, actually
More than that. If in a path you are moving away from the target, it can be more than that, but this is
It will be log n to the base 2 plus 2, because you only expect to which 1 bit per
the way you put it. Okay, that is not necessarily true. Suppose if someone says that you need only this L is 30, say, then you can say that I use only 5 bits. The 0 0 0 0 0 combination I will be using to indicate empty cell, 1 1 1 1 1 combination I will be using to indicate obstacles, and the other numbers between means 1 and 29 that will be using for that. So, it is actually L plus 2 log 2 of that, how many bits are required for that. Now, with respect to memory requirements, some interesting improvements have been suggested. See, just if you look at the way Lee's algorithm works, well, we have labeled the number 1 2 3 4. Why? Because during retrace there is no ambiguity where to return back. For each particular cell which has been labeled, the successor and the predecessor, they have two different numbers, because if I have I, the successor will be I plus 1, the predecessor will be I minus 1. So, during backtrace I exactly know where to go, right. But suppose instead of this 1 2 3 4 5 this kind of numbering, well, I use an alternate numbering. How? 1 2 3 1 2 3 1 2 3, in that order I repeat. 1 2 3, again I use 1 2 3, again 1 2 3. So, if I use a numbering scheme like this, suppose I am currently labeling the cells with this number 3. then I know with respect to 3 my successor will be labeled as 1, my predecessor will be labeled as 2. So, at each level my successors and predecessors are distinct. So, as long as I can distinguish between my predecessor and successor, it is fine. So, I can reduce the number of bits required per cell if I use a labeling scheme like this 1 2 3 1 2 3 1 2 3. So, I can very uniquely distinguish between the predecessor and successor, and here I will be requiring 3 bits per cell because it is log 3 plus 2. The ceiling of that will be 3 bits.
And also we require memory for memorizing that which is my predecessor and which is my successor.
That is the number you are putting now. Suppose you are labeling a cell with a number 3, then you search its neighbors. Some of the neighbors will be labeled as 1, some of them will be labeled as 2. You know 2 is the predecessor and 1 is the successor. During retrace you will always move from 3 to 2, 2 to 1, 1 to 3, 3 to again to 2, in that way.
Sir,
yes.
now I have a fundamental doubt. In a BFS graph,
Huh.
if you do a graph of a BFS of a graph,
Okay.
at a particular node you can land up from 2 different paths.
In breadth first search, at a particular node you can land up from 2 different. Yes, you can.
Okay.
Huh.
So the value number you are assigning to a particular node will be different. It might be different for 2 different paths.
It might be different from 2 different paths, but
Then what will you
see,
solve for that?
yeah, I am telling you this is. So your question is that the way you are labeling, the label of a particular cell might be different for 2 different paths,
Yeah.
but the shorter path I have already labeled first.
Okay.
Once I have labeled, that cell is not a candidate for relabeling.
Okay, you visited
Huh.
something.
Visited sort of thing.
But sir, that can happen that the first path did not land on the target, but the other path can.
But yes, sir, that was a longer part, but it will land on the target.
No,
Yeah.
It's a cycle. You can
No, it can land on a target, but not via that cell.
Yes, sir.
It can have some other path and land into the target from there. Okay. Okay. So there is another interesting improvement to the Lee's algorithm, that you don't use 1 2 3, just use 2 numbers 0s and 1, and you use a labeling scheme like this 0 0 1 1 0 0 1 1 0 0 1 1 in this order. See, in this sequence you again observe, say 0 0 1 1 0 0 1 1, in this order it goes on. You take any number, say you take the second 0, the predecessor is 0, successor is 1, they are different. You take this one, predecessor is 0, successor is 1, they are different. You take the second one, predecessor is 1, successor is 0. So for each particular step the predecessor and successors are different, but you will have to remember that which 0 or which 1 you are in, is it the first one or the second one? That you will automatically remember during backtrace or forward trace, you will be remembering that anyway. But the way we are labeling, the predecessor and the successors, they are always different, one of them is 0, other is 1. So during backtrace there is no ambiguity. So if you do this, the number of bits becomes only 2 per cell, log 2 plus 2. Okay, just I am taking an example to illustrate this process with the same example. Right. From the source you start with zeros. The red color indicates the first 0, okay. Then again another 0, I am indicating with a different color. Then 1, the first one, then the second one, yeah, this you can keep just by using a single flag, whether it is odd or even. During forward trace you just remember that, nothing else, whether it is the first one or the second one you are labeling. Similarly 0 0 0 0, this is the first 0, then the second 0, then the first one, then the second one. So, finally, you will see that you land up the target with the second one. So, now during backtracking you will be remembering this, that you have reached T with the second one, which means your predecessor will be a 1 with respect to 0 0 1 1 this subsequence, you have landed up with this one. So, the predecessor will be a 1. So, from here search for a 1 in the neighbor, you come here, from here you search for a 0, come here, from here you search for another 0, come here, then come to a 1, then 0, then finally you reaches. So, just if you remember this is the first one or the second one, backtracing is easy, right. So, this is an improvement of Lee's algorithm you can have with very little. But previous one?
Just this one, example you said.
Yeah. This example one, okay.
Yeah.
Yes.
In the if you go from third from the bottom and the first column.
This one.
Third from the bottom and the second column you this 0, this 0, yeah.
Yes.
This 0 you can reach from a 0 and you can reach from a 1.
Yes.
Okay.
But yeah.
Again there is the same ambiguity, like you
No,
are doing 2 paths and now you
there is
are
no
not
ambiguity. The
sure which
first one you are labeling. See, there may be another path. Or see, means finally this S can also label it following some other path round this, round this, round this, round this. But this is the shorter path which has reached this cell first. Okay, after reaching it, it has already labeled it with some number, and any other wavefront coming from some other direction will not disturb it any further. So, here what I am saying is that the shorter wavefront, whenever it hits you, you just store that with you. Now, if anyone else hits you later, you ignore that. That way, I will always keep track of the shortest path of every cell from the source. Okay. Fine. There are a few other heuristics which are used to improve the running time of Lee's algorithm. This is with respect to memory, but the number of cells you have to label, that can grow very large, you can easily understand. So, there are some heuristics. What I am saying is that whatever we have talked so far, that is with respect to the memory requirement, but with respect to the running time, the execution time will depend on how many cells we have to label during the breadth first search scheme. So, if we can reduce that by some means, then the you can say the execution time will be faster. So, there are several heuristics which have been proposed to reduce the running time. The first one says that you should choose the starting point suitably, that means one is source and one is target, fine, but which one you should select as source and which one as target, that will influence the running time. How? Suppose you have the grid array like this. Okay, one of the points you want to connect is towards the corner and other is towards the center. Now, if you select this as the source and this as the target, then your wavefront will move in all possible directions starting from S. But if you choose the other way around, if you choose the one near the corner as the source and this as the target, then the boundary will clearly not allow the wavefront to expand in all directions. So, the number of cells you will be labeling will be much less, 1/4 of this approximately. So, the first heuristic says that you choose a point near the corner as the source, choose the starting point as the one that is farthest from the center of the grid. The second one says, well, from the source, as you go on expanding, the number of cells you need to handle becomes larger and larger and larger. So, as the second heuristic, why do not you propagate waves from both the directions? Start from source and target both, and as soon as the two wavefronts touch, you stop, and from that touching point you backtrace in two directions. This is the other way around, this is double fan out. Propagate waves from both the source and the target cell, labeling will continue until the wavefronts touch. And the third one arises out of a realistic constraint. Say the realistic constraint says, suppose in this grid array we want to interconnect a point out here and a point out here. Now normally I would not have a path which will go like this, then this, then this. Normally if you imagine a rectangular bounding box, certain percentage beyond that, say 10% or 20% beyond that. So you can say that I will not allow my net to go beyond that. This is a realistic constraint. This is called framing. So an artificial boundary is considered outside the terminal pair to be considered, to be connected, and you can have some figure 10 to 20% larger than that. You will not label cells which are beyond that. So by using these heuristics you can improve the running point of the Lee's algorithm, running time.
But in this case we may not find a solution.
In this case you may not find a solution, obviously. Yes. But if you do not find a solution, you can expand that imaginary box and you can again rerun it. So just one thing we will see later, that these kind of grid routing algorithms are used only occasionally. These are not used for routing all the nets. These are typically used to route the difficult nets. Okay.
Sir,
yes.
in this method between the two routings,
Huh.
you are not showing any information.
Between the two routing means?
Like we have a pair of SNT and
Huh.
we have another pair of SNT.
Huh.
So if we store the information which we have gathered in the first search, that can be used in the searching in the second.
No, that we are not storing. We are not keeping any history.
But that will help.
That might have helped. It means they are modified.
You are learning and again forgetting the rules.
Yeah, we are forgetting again. Yes. True. So one thing you can slightly modify Lee's algorithm to handle multi-point nets also. Say so means a multi-point net is a net which will be connecting 3 or more terminal points. Now a simple extension of Lee's algorithm can handle this. How? See, the extension of Lee's algorithm will work like this. So one of the terminals of the net will be treated as source like the previous one, and from there you start propagating wave till it hits one of the other points. So you have a partial net already laid out. Now all the grid cells you have already found out as part of this, all these cells will be acting as the source for the next step. So actually you are not starting from scratch in the next step, you are starting from this partially completed layout, and from all these points you are starting to propagate the wavefront to touch the new points. And this process continues till all of them touch. I have a small example to show you. Suppose I have a scenario like this, A, B, C and D, they all belong to the same net, they all will have to be connected, and incidentally A and D are at a distance 1, 2, 3, 4, 5, 6, 7, B is also at the same distance 1, 2, 3, 4, 5, 6, 7. So in the first step itself, when you apply Lee's, you will possibly find a path like this and also find a path like this, right. In the next step what I am saying is that, say initially A was the target, now source. Now in the next step when you are wanting to reach C, not only A, all the other cells which have been marked, they will all act as sources. So wavefront will go out from all those things and the nearest one to touch, so nearest will be from either D or C, both will be there. So you take one of them to reach C, right. So just by using an extension like this you can just have.
So in this case, you can also have a smaller path from D to B set. You know, A to B, you can have from D to B.
So we can talk of subtracting from B to AD.
Remove A to B and
Yeah, but the way you are doing it, you are not taking that into account. In that case, you will have to rip up this net, because your basic data structure is not efficient to do all those things.
Yeah, what we can do is we just take a single target first, and then we can from that target to the source we can start from all the points. Then from here you can just take a target with D, sir. From A to D.
Okay, fine. So instead of having it from A to D and B both, you take any one of them at a time. From there, okay.
That will be much better option.
That's the other alternative. You take AD, and from AD path you try to reach B and C. Don't take both these at the same time.
Only one there, sir.
Only one you take. Fine. There is another maze routing algorithm we will be discussing, but that will do next class. See, there the concept is slightly different. We will not be doing a blind search like the Lee's algorithm. See, this breadth first search or depth first search, these are blind search algorithms. We really do not know which side our solution lies. We are exploring in all directions, we are exploring all possibilities. Now, we will be looking at an algorithm which is more like a goal directed search. Well, we have the xy coordinates of the source and the target. So, as we go on labeling the cells like we are doing in Lee, so we also know whether we are moving in the correct direction or moving out towards the wrong direction. So, we define something like a cost function if you are moving away or not, because if you are moving away one step, then to reach the target we again have to come back one step somewhere later. So, more you move away, you will have to move back that many steps to reach T. So, this will be a priority kind of a thing. That means you try to always move along direction where you are not moving away from the target. Well, in some cases you will have to move away from the target, you will try to minimize that. How many minimum number of cells you can move away from the target and still you can manage that. Now, this is the basic idea behind the Hadlock's algorithm, and this we will be discussing in our next lecture.